There are few ideas in history that feel as obvious to us today as this one. The Earth goes around the sun. We learn it early, we repeat it casually, we treat it as basic fact. But in the 16th century, when Nicolaus Copernicus argued for that very idea, the real question was not whether it sounds true to us now. The real question was this: what did he actually have to support it? And the answer is more interesting than most people realize. Copernicus did have scientific reasons. He had observation, he had mathematics, he had patterns in the sky that made far more sense if Earth was moving. But he did not yet have the kind of evidence that could instantly silence his opponents. And that is what makes his story so compelling. He was not a man who won because he had one spectacular proof. He was a man who saw that the old explanation was becoming harder and harder to defend. For centuries before Copernicus, the dominant picture of the universe was the geocentric model. Earth fixed at the center, with the sun, moon, planets, and stars all moving around it. It was not simply superstition. It was a serious intellectual system, refined over generations, and it matched ordinary human experience. The ground beneath our feet feels still. The sun rises and sets. The stars appear to circle overhead. To most people, it was the heavens that moved, not the Earth. But the planets were a problem. Unlike the stars, they did not move in a simple, steady pattern. They wandered. Sometimes Mars, Jupiter, or Saturn would appear to slow down, stop, move backward for a time, and then resume their normal path. This strange behavior is called retrograde motion, and then resume their normal path. This strange behavior is called retrograde motion. Ancient astronomers could account for it, but only by building an increasingly elaborate system of circles upon circles. Epicicles riding on larger circles, all carefully adjusted to preserve the idea that Earth remained at the center. Copernicus looked at that confusion and asked a radical question. What if the planets were not the ones behaving strangely? What if we were moving? In his model, retrograde motion was no longer a real reversal in a planet's path. It was only an appearance created by Earth's own motion. When Earth passes an outer planet, that planet seems, for a short time, to drift backward, much like a slower car seems to slide backward when you overtake it. Suddenly, one of the most awkward features of the old system became something natural and expected. Copernicus had not discovered a brand new phenomenon. He had found a better explanation for one people had been watching for ages. And retrograde motion was not the only clue. There was also the curious behavior of Mercury and Venus. These two planets never stray very far from the sun in the sky. They appear only near sunrise or sunset, as if tethered to the sun itself. In the geocentric system, that pattern could be reproduced, but it felt artificial. In the Copernican system, the reason was simple. Mercury and Venus orbit closer to the sun than Earth does. From our viewpoint, they would naturally always appear near it. What had looked like an odd restriction now became a direct consequence of the system's structure. This is why Copernicus mattered so much. His great strength was not that he brought the world a single crushing observation. His strength was that he reorganized the heavens into a more coherent whole. In his system, the order of the planets made more sense. Their periods made more sense. Their strange motions made more sense. The whole universe began to look less like a patched machine and more like an intelligible arrangement. As the Stanford Encyclopedia notes, one of Copernicus's major achievements was tying the order and periods of the planets into a single unified system centered on the sun. But here is the crucial point. A better explanation is not automatically a proven explanation. A careful critic in the 16th century could still respond, "Very elegant, very clever. But how do you know Earth actually moves?" And that was a devastating question. Because if Earth truly traveled around the sun, then the stars should appear to shift slightly. Yet no such shift could be detected in Copernicus's time. To many scholars, that seemed fatal. If the Earth moved, why did the stars not betray that motion? Copernicus's answer was bold. The stars must be unimaginably far away, so far that the shift was too small to detect. Today we know he was right. But at the time, that sounded less like proof, and more like a daring rescue of his theory. Copernicus still believed that heavenly motion had to be built from perfect circles. So, even though he put the sun at the center, he did not entirely escape the old complexity. he still used epicycles, and his system did not immediately overwhelm older astronomy with obviously superior predictive power. His system did not immediately overwhelm older astronomy with obviously superior predictive power. Even the Stanford entry notes that his manuscript had numerical inconsistencies, and that much of his mathematics still depended heavily on inherited astronomical traditions. That is exactly why the debate did not end with Copernicus. One of the most important responses came from Tycho Brahe. Tycho proposed a compromise system. The Sun and Moon went around Earth, while the other planets went around the Sun. Copernicus had made the sky more understandable, but not yet in a way that forced everyone to surrender. What finally changed the balance was not one person, but a sequence of breakthroughs. First came Galileo. In 1610, using a telescope, he saw moons orbiting Jupiter. That mattered because it shattered the old assumption that everything in the heavens must revolve around Earth. He also observed the phases of Venus, which showed that Venus orbits the Sun. At that moment, heliocentrism stopped being only a beautiful way to organize the heavens. It began to accumulate direct observational support. Then came Johannes Kepler. Working with Tycho Brahe's precise observations, Kepler discovered that the planets do not move in perfect circles at all. They move in ellipses, with the Sun at one focus. That was a decisive advance, because it corrected one of the biggest weaknesses in Copernicus's model. Kepler's breakthrough transformed heliocentrism into a far more accurate mathematical description of how planets actually move. And finally came Isaac Newton. Newton explained why the planets move as they do. In 1687, by uniting terrestrial and celestial motion under the law of gravity, he gave the Copernican picture a physical foundation. By then, heliocentrism was no longer just the cleaner model, it was the deeper one. So when we ask whether Copernicus had real scientific grounds for heliocentrism, the answer is yes. He had patterns and mathematical coherence. But if we ask whether he had the kind of evidence that could instantly convince the world, the answer is no. And maybe that is the real lesson of his story. Science does not always advance because someone arrives holding a final proof in their hand. Sometimes it advances because someone sees, before anyone else, that the old explanation is no longer enough, and dares to build a better one. Copernicus did not defeat the old universe in a single blow. He made a new universe thinkable. And then history caught up with him. Like, subscribe, and hit the bell icon for more.